Hello, my statistics students. Today we're going to discuss and consider probably the most important topic in this semester, but unfortunately at the same time the most complicated. And the thing is that it is really abstract. We can only imagine the things that we're going to discuss today. And I can really tell you, according to my experience, this is the most difficult topic for all the students in the world from Australia to Alaska. So this is called sampling distributions and the central limit theorem. So we will start our discussion. What I want to tell you first is that in statistics we have three different distributions. The first distribution is called population distribution. Now the second one is sample distribution, and finally, and most important for today, sampling distribution, and all of these distributions are different. So imagine that we have a population of the values, for example, the population of all the students at our university, there's about 10,000 uh, students, and that we consider the height of all these students. Now, if we consider all the elements in this particular population, we call this population distribution. So this is population distribution, which means the distribution in a single population. All right, so this is distribution of all elements in the population. Next, we are going to draw a single sample from these populations, for example, 40 students. And now we focus our attention only on this particular sample, and we think about these 14 elements. And when you consider what's going on in the sample, the distribution in a single sample, we call that sample distribution. So this is a distribution of a single sample. So what is the sample distribution? Distribution of data in a single sample. So this was very easy, both of these definitions. However, now we are coming to something really very, very difficult that we can only treat as some imaginary process. So what is going now is that we need to imagine the following scenario. So we have a population of all the values, and now from this, which has mean, for example, mu, and the standard deviation of this population is sigma. Now we are going to take a single sample from that population and to calculate its mean, the mean of the sample, which is x bar 1. Now we take a second sample and we calculate the mean x bar 2. These samples must have the same size. And now, can you imagine a process like that going on forever, depending on the sample size? Finally, we can also take 1 trillionth sample from that population and calculate x bar. So what we're going to do now is the following. Now we focus on these x bars, not on the population, not on the sample, but on these x bars. So with x bars, we take a single sample, as we said, x bar 1, and we plot this x bar. Now another sample, we have a different x bar 2, x bar 3, x bar 4, x bar 5, and so on, zillions of these different uh, sample means. The most important question now is the following, or better to say, there are three important questions. So the first question is how we're going to call this distribution of x bars of all these possible samples and their means. We are going to call this sampling distribution, not sample, not population, but sampling distribution. Hence, to make an overview of all this so far, we have a population distribution in statistics, sample distribution, which is a distribution of a single sample, and sampling distribution, which is a distribution of all possible sample means that we can take from a single population. All right, so definition, sampling distribution sample means is distribution of the means obtained from all possible samples, all possible samples. All right, now let's focus again on this distribution of all x bars. There are three questions. The first question is, what is sitting in the center of this distribution? What is the center of this distribution? This is the first question. And it will come as a surprise to you, but the center of all these sample means is nothing else but the population mean mu. So in the center of all possible x bar, we have the mean of the original population. So this is the first important thing that we need to understand. So there is a relation between the distribution of all these x bars, which is called sampling distribution, and the mean of the original population, which is mu. So this is the first important thing that we need to consider here and to understand. Now the second question is, what is the standard deviation of this sampling distribution? In other words, what is the spread? What is the spread of all these x bar? Is it big or is it small? And quite interestingly, also there is a relation between the spread of all these sampling distribution of x bars or distribution of all x bars and the original standard deviation of the original population. So we are going to introduce a special notation for this standard deviation of x bars, sigma x bars. So this is standard deviation of all x bars. Now there is a formula that we need to understand because we are going to apply this formula many times from now onwards. This can be calculated as sigma divided by the square root of the sample size n. So let's now focus our attention on this. On the left-hand side of this formula, we have sigma x bar. This is, as I said, so important that it requires a special terminology, a special term. So from now onwards, we are going to call sigma x bar standard error. So this is standard error, standard error, standard error. So standard error is sigma or the square root of n. In this formula, sigma is the standard deviation of the original population, and n is the sample size. So this is the second rule, the second property of the distribution of x bar. Is this the central limit theorem? No, it is not. So we need now to ask ourselves the third and last question, and that question is what is the shape of this sampling distribution of X bar? Is it some kind of weird shape, or maybe there is some kind of regularity that we can observe? So, question again, the third and most important question for us, something that we'll be using and using hundreds of times from now until the end of the semester, online semester. So question again, what is the shape of that sampling distribution? And the answer is obviously that the shape depends on the shape of the original population. So if original population is ugly, the shape of sampling distribution will also be can be very weird or strange. If the shape of the regional population is symmetric, most probably the shape of the sampling distribution will also be symmetric. So now let's finalize this discussion. So if the regional population is normal, then the shape of sampling distribution of X bar is also normal. Is normal for any sample size. Probably this is something to be expected. Is this the central limit theorem? No. Now we are ready for the most important thing and difficult thing, and that is to give a definition of the central limit theorem. This time we will observe any population with any possible distribution. So if the original population is not normal, sorry, in other words, it can have any possible shape, the shape of the sampling distribution of X bar is approaching what? It's approaching normal distribution. Normal distribution. When the sample size is large, so the question obviously is what is the large sample size, and the answer is when the sample size is larger or equal to 30. So this is the central limit theorem, the most important statement in statistics and probably in mathematics, and mathematicians and statisticians have tried to prove this for many hundreds of years, and finally it was proved by some Russian mathematicians, the final version of the central limit theorem. So again, let us try to understand this. So this time we think about any population. So this is our population of all the values, and we can imagine any weird population like this one, for example, something very ugly. And from this population, we repeatedly take samples, all possible samples of the same size. We calculate X bar 1, X bar 2, blah, blah, blah. And then we consider the distribution of these X bars. This is called sampling distribution. And regardless of the shape of the regional population, the most beautiful thing and conclusion in statistics is that the shape of these x bars will approach normal distribution. So the distribution will not be exactly normal. The distribution of this sampling distribution will approach, can be approximated with the normal distribution. Not for the small sample sizes, no. For example, for the sample size n equals 5 or 6 or 10 or 15, no. For the large sample sizes, what is the large sample size? 30 or over. Okay, so let's now give an overview of the central limit theorem. So for you, the easiest and the most important thing would be to consider when are you going to apply this central limit theorem. And the answer is if the sample size is large. So you are going to read your problems and to see whether the sample size is smaller than 30 or 30 and larger. If it is 30 or large, then you will be happy to say, hey, I can apply the central limit theorem. All right, so the central limit theorem is valid in two cases. Case number one, the original population is normal, hence the sampling distribution of x bar will also be normal, regardless of the sample size, even if the sample is 2, 3, 4, 5, blah, blah, blah. And the other case is when we have any kind of the regional population and we are dealing with a large sample size, which is n larger or greater than 30. So my suggestion for you will be now, this is so important, whenever you want to do any research or survey in statistics, please try to use large sample size, which means what? Which means, for example, you want to find out something about your students, then always take at least 30 students. Why? Because then you can happily and gladly apply the central limit theorem. So this is the most important fact in statistics. All right. Now, what I would like you to show is some cases to try to understand, to apply this theoretical knowledge. Once again, this is so difficult to imagine, any kind of population distribution. Then you take repeatedly in your mind, you take many different samples. Then you create distribution of the x bars of those samples, and you think about the shape of that distribution. This is really very difficult. And when I was a student, it was for me very difficult, almost impossible to understand. So don't worry. The nitty-gritty is that what you need to do, once again, read your problem, see whether you have sample size n 30 or larger. If you have, apply the central limit theorem. All right. So what we're going to do now is to try to understand the central limit theorem better, or maybe I can call this central limit theorem in action. All right, so we'll be using now some simulations from the site that was made by the famous Professor Agresti from the Florida State University. And thanks goodness that we have now these interactive web pages. In the past, this was a nightmare for the students. Students were not able to understand anything about the central limit theorem. So this is now really great. So what we're going to do now is first to select some population and let it be uniform. What is the uniform population? This is the uniform population. All frequencies are the same. and the mean of that population is 15. So what I'm going to do now is to take a sample from this population, a single sample. Click, draw sample. All right. So here, this is original population. This is distribution in a single sample, size 20. And this is sampling distribution of the sample means. Currently, we have only one sample, and hence we have only one X bar. So mu 50 is the original mean of the original population. See, 50, and X bar is the mean in our first sample. Now we cannot conclude anything about that. We have to pretend that we understand now, to apply our mind and to take many different samples from this population and to see. So this, we have to focus on this to see, to look and to observe the shape, what is going on with the sampling distribution, with the distribution of the sample means. So what I'm going to do now, I'm going to take 10,000 samples. So draw samples. And look what is happening. Even when the sample size is just 20, the shape of the sampling distribution is normalish. So we have taken a uniform distribution, which is far away from the normal distribution, and the distribution of X bar is really normalish. Now I'm going to take something a bimodal distribution. Look at this. This is far from being normal. And I'm going to take 10,000 samples from this distribution. So very small samples of size, for example, 5. Draw samples. And still, can you imagine what is happening? The distribution, the sampling distribution start approaching normal distribution even for the sample size of 5. It is really unbelievable. And now, and the original population is bimodal. Now I'm going to make, to build my own distribution, or no. I'm going to take a skewed distribution like this one, and to take 10,000 samples from this distribution. Okay, draw samples. So what is happening? This is not normalish. Why? Because the population is not symmetric, the population is skewed. To the left or to the right? Oh, I can hear you. To the right, of course. So this distribution is not normalish. Why? Because we are dealing with the small samples. The sample is only 5. Now I'm going to increase the sample size and make it 30. This is a magical number from the Harry Potter movie. 30 is the magical number in statistics. I'm not sure what is going to happen now, but I will draw samples now. Okay, draw samples. So look what is happening. Look what is happening now. The sampling distribution of X bar is approaching normal distribution. And look what is the center, what is sitting in the center, what is sitting in the center of the sample distribution. Nothing else but the mean of the regional population, which is 10. This is rule number 1. The center of all the sampling, of all the sample means, is nothing else but the mean of the regional population. And finally, statistics in action, real population data. What I'm going to do now, I'm going to take the distribution of, for example, world life expectancy before this corona virus, and you can see that this is heavily skewed to the left, and it is based on the life expectancies, both females and males, from 198 countries. All right, so let's take samples of size 30 and 10,000 samples, or I can take just one, just to show you once again. So this is distribution in a single sample. This is original population made of the distribution of 198 countries. And this is this sampling distribution. Currently, we have only one sample. So currently, we have only one X bar. And now to increase the number of samples that we're going to take from this population to 10,000, and let's observe what is going to happen now. I'm going to get the normalish distribution. So draw samples. Unbelievable, isn't it? So can you really imagine the excitement of the early mathematicians and statisticians in the 18th century when they realized this amazing fact? This is really unbelievable. So hopefully now you understand much better the notion of the central limit theorem, and we'll go back to our okay. So again, here what you have on page 3 of the handout, you have different populations, different distribution, different populations. So for example, this one is uniform. So if you take the samples just of 2 elements, see what is going to happen. If you increase to 5, it looks like normal distribution, 30, normalish. Now, weird distribution like this one is the original population. Sample size is 2, something weird. You increase to 5, looks like normalish. And finally, this, heavily skewed distribution. You take a sample of size 2, this is not normal. Size 5, this is not normal. Size 30 looks like approaching normal distribution. And again, when the distribution, original distribution is normal, X bar is always normal for any sample size. Now I will finalize this with 2 exercises. So the first exercise is the following one. So deer mice have a body length known to vary with the mean body length mu equals 86, and the standard deviation is 8 millimeters. We take random samples of 100 deer mice. All right, now we have some questions here to see whether you understand this most important topic in introductory statistics. So first question, what is the shape of the original population? Let's see the problem. Are we given this information? No. So we have no clue. What is this? So no clue. Next, what is the mean mu of the original population? And if you take a look at the problem, the mean of the original population is 86. So mu equals 86 millimeters. Next, question 3. What is the standard deviation sigma of the original population? Now you can find the answer in the problem. Sigma equals 8 millimeters. All right. Is this the central limit theorem 1, 2, 3? Of course not. Now for what is the mean of the sampling distribution? In other words, if we take all possible X bars from the population, what is sitting in the center of that sampling distribution of X bars? And that is rule number 1. The mean of the sampling distribution is nothing else but the mean of the original population. So the mean of all X bars is nothing else but the mean of the original population, which is 86 millimeters. Is this the central limit theorem? No, I know that you know that it isn't. Question 5. What is the standard error of the sample mean? Aha! Standard error. What is the standard error? In Newton that we introduced today, standard error is sigma of x bar, which is equal to sigma over the square root of n. All right, so this is standard error of the sample mean. This is rule number 2. Remember, we have 3 rules here. What is sitting in the center of the sampling distribution x bar is rule number 1. What is the spread? Standard error. Rule number 3, central limit theorem. All right, so let's calculate this. Sigma is 1/8 divided by the square root. What is the sample size? 100, which gives 0.8 millimeters. And finally, the central limit theorem. The question of the central limit theorem. What is the shape of the sampling distribution of the sample means and why? What is the shape? In other words, can we apply the central limit theorem or not? So let's have a look at this problem. And whenever you're asked about the central limit theorem, just think about the sample size. Is it 30 and over or smaller than 30? If it is 30 and over, yes, you can apply the central limit theorem. If it is smaller, it is small sample size, so you cannot apply the central limit theorem. All right. So in this case, the sample is 100, which means what? Which means that we can apply the central limit theorem, of course. All right. So what is the shape? What is the shape of the sampling distribution? The shape is normalish, approximately normal. Why? Because of the most important statement in statistics. And that is the limit central limit theorem. In other words, n is larger than 30, n is 100. So that is the story of the central limit theorem. And I'm going just to do one more example to show you how you're going to use your calculators to obtain the functional knowledge of the central limit theorem. All right, so I think that I will do just example 1. Okay. The heights of 18-year-old men are approximately normally distributed with mean 6 to 8 inches. Okay. And standard deviation 3 inches. So this is a real world example. Question A. What is the probability that a single 18-year-old man selected at random is between 67 and 69 inches tall? In other words, this probability is asked. What is the probability that when you select a single person, that his height will be between these two? So how are we going to solve this? And the answer is, I hope that you remember the function that we used just before the break. That was a long time ago, 200 years ago. All right, so that is normal CDF. Normal CDF. And this function has 4 team players. The first team player is start. So what is the start here? 67. The second team player is end. What is the end here? 69. The third argument is the mean, and the mean is 68. And finally, the last argument is standard deviation sigma, which is 3. All right. So when you plug in these values in your calculator, you will get the result. The result is 0.2611. Did we apply the central limit theorem here? No. Why? 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 Because we have a single element taken. We have a sample of just one element. How can you apply the central limit theorem when you have just one element? It is impossible. All right, so this is in this A example, we applied our knowledge that we built just before the break. All right, and the final task for today is question B. If a random sample of nine 18-year-old men is selected, what is the probability that the mean height is between 67 and 69 inches? So just now focus on the question. Probability that, what is the difference now between this one here and this one here? The difference is that in the previous example, we are talking about the single element, a single element. Here, we have something very, very different. We have X bar. So when you have X bar, you think whether I can apply the central limit theorem or not. All right. So let's have a look. Can I apply the central limit theorem? A random sample of 9. So random sample of 9, n equals 9 less than 13. So I cannot apply the central limit theorem. Great. Wrong! Why? Why? Because look at the sentence. The heights are approximately normally distributed. What does it mean? It means that the original population is normal. So when the original population is normal, you can always apply the central limit theorem. Always, always, always. It doesn't matter what is the sample size. So yes, here we can apply the central limit theorem. So let's calculate this using our calculators. I want to show you the significant difference. There's just one difference between using the central limit theorem and in B and A. So practically for your exam or for your test, you just need to make one slight adjustment in the normal CDF function. Okay, so normal CDF, normal CDF. The first argument is start, the second end, then mu and sigma. This is how we treated this so far. So the start is 67, end is 69, mean is 68, and sigma. Are we going now to enter 3? What is going on? And the answer is that now you are asked to find the probability of X bar. So the only difference between the application, this section of the central limit theorem, and everything that you knew so far is this last guy here. So this is the only difference. So whenever you're going to apply the central limit theorem, think about this guy here. It is not going to be sigma. Instead of sigma, what we're going to do? Distribution of x bar. What is the sigma of x bar? Sigma of x bar is standard error, which means what? Which means instead of sigma, you're going to do just this tiny adjustment, sigma over the square root of n. Sigma over the square root of n. This is the only difference between the thing that we... So the practice of the central limit theorem is so unbelievably easy. Just divide this last argument in this function by the square root of n. You don't need to know anything about the theory. Who cares about the theory? All right. So when you do something like this, you will get square root of n. In this case, is square root of 9, which is 3. So sigma is 3 divided by 3 is 1. So the last guy here will be 1. And when you calculate using your Texas Instrument calculators, you will get the result is 0.6826. Now, I hope that you're ready to go on with and do yourself example 2, example 3, and so on. Good luck. Actually, you don't need any luck. You just need to apply everything that we have covered so far. So thanks for watching the most important topic, and stay healthy, stay safe, and again, say hello to your family